In section 8.2, instead of drawing all of the vectors out, we're going to represent the vectors algebraically using an ordered pair. And we talked about this a little bit in the last section. The ordered pair 3, 5 is a vector in standard position, which means it starts at the origin and it ends at 3, 5. So basically it goes over 3, up 5. Now there are lots of vectors that could be 3, 5 because as long as it has the same magnitude and the same direction, it's equal. This one's also 3, 5 because it goes over 3, 5. This one goes over 3, 5, 3, 5. All of those are the same vector. Typically though, when we write an ordered pair 3, 5, we mean the one that starts at the origin. We mean this one. It wouldn't have to start there though. We can write an ordered pair that represents a vector that goes from -3, 5 to 4, -2, and then we're going to find the magnitude of that vector. Take a minute to write that example down, and then we'll work on it together. If it helps, you can draw it out. This vector is starting at -3, 5, and ending at 4, -2. So that vector is not in standard position, but I can still write an ordered pair for it. It goes over a certain amount and then down a certain amount. To figure out how much it goes over, I'm looking at how much it changes in the x direction. In the x direction, I change from -3 all the way over to +4, so that's a change of 7. In the y direction, it changes from 5 to -2. So in the y direction, it changes -7. It's going down 7. So that's the ordered pair that represents that vector, 7, -7. Then they want the magnitude of it. The magnitude would be the length of the vector. So I'm going to draw this vector out. I have a picture of it up here, but I'm going to draw another one that's more in standard position. It starts at 0, 0, it goes over 7, down 7. If I want the magnitude, I need the length. Since the 7 and the -7 are the horizontal and vertical components, they make a perfect right angle, so we can find the magnitude by doing the Pythagorean theorem. And since this one is isosceles, you can also figure out the magnitude using the shortcut. The magnitude is 7 square root of 2. You can add, subtract, and multiply vectors by a scalar or by a number, and when you do that, it works exactly like you think it should. I wouldn't write down these rules because they're pretty obvious. When you add vectors, you're just going to add the x's and add the y's. Same thing when you subtract, you're going to subtract the x's, subtract the y's. And when you multiply by a scalar, you're just going to distribute that scalar to both parts. Instead of writing down those rules, write down this example. Let m equal 5, -7. N is 0, 4, and P is -1, 3. And then we're going to do some computations. I'll do the first one, and then I want you to try the other 3 on your own. For the first one, if I'm going to do m plus p, I'm doing 5, -7 plus -1, 3. And vectors are nice to add. To add them together, you just need to add together the x's and add together the y's. So m plus p equals 4, -4. You're going to do the exact same thing on b, except for you're going to subtract. On c, you're going to just multiply a 7 times both parts, kind of like distributing. And d just has a couple parts. First, you're going to distribute And then you're going to add and subtract the x's, and then add and subtract the y's. Pause the video and see if you can do those 3 examples on your own. Compare your answers for B, C, and D with what we have here. Hopefully you had them all correct. Alright, most of the homework in this section is like these, where you're just adding and subtracting vectors together. There's also another vocab word, which is unit vectors. Unit, like unit circle, means 1. So a unit vector is just a vector that has length 1. And they say a vector along the x-axis that has length 1 is called an I. A vector that has length 1 along the y-axis is called a j. So instead of x and y, it's I and j. What they're saying is if you have any vector at all, you can always rewrite it as the sum of unit vectors. You can write it as plus however many i's you need, and then plus however many j's you need. It's kind of a silly thing. Engineers use it a lot. But what they're saying is a vector 3, 4, instead of writing it as 3, 4, which is this vector, you could rewrite it as 3 i's plus 4 j's. So you could rewrite it as 3i plus 4j. It's just another way of writing it. So this is, probably call it vector form, or as an ordered pair. And this is as the sum of unit vectors. So we're kind of going back and doing an example that we did before, but now we're just going to write the answer as the sum of unit vectors instead of as an ordered pair. Write AB as the sum of unit vectors if A is at 4, -1, and B is at 6, 2. Again, you could draw it out if that helps you. You wouldn't have to draw it out, but you could make a picture of a vector that's going from 4, -1 to 6, 2. If I'm going to write it as an ordered pair, which is what I like to do first, I need to figure out how much does it change in the x direction and how much does it change in the y direction. In the x direction, it changes by 2, and in the y direction, it goes up 3. So as an ordered pair, or in vector form, it's the vector 2, 3. To change that to the sum of unit vectors, it'll be 2i plus 3j. The homework in 8.2 is on page 497. The 8.3 stuff is very, very similar, but in 8.3 it's 3 dimensions. So instead of just an ordered pair, we'll have ordered triples. And we are going to do that section today also.